Okay, so we're going to look at the nature of roots. So by the nature of roots, what we mean primarily is whether the roots are real or not, and then if they are real, whether I have two real roots or whether I have two equal real roots. So kind of one real root or one repeated root. And what we're going to use to find these is what we call the discriminant. And the discriminant is your b squared minus 4ac, which we should kind of note as the part under the square root in your quadratic formula. And the reason this tells us so much about the behavior or the nature of the roots of the quadratic is if you think about it, that square root is quite an important part, and it's the part after the plus or minus. So if that part is greater than 0, if we have something under the square root, then what I get is two distinct or different real roots. So two different real roots. If that part is 0, then I'm just going to get equal real roots. Okay, so kind of like one solution. And it all comes back to the fact that if this part is 0, then I'm not adding or subtracting anything in either case. So I just end up with two of the same root. If b squared minus 4ac is less than 0, I get two imaginary or complex roots. And that comes down to the fact that the square root of a negative number is a complex or imaginary number. Now, we haven't done that completely. That's something we will come to a little bit later. But just having that idea in your head is important. The square root of a negative number is a complex number, so if b squared minus 4ac is less than 0, I get two imaginary or complex roots. And another way of framing that is we have no real roots. The last little part then is if b squared minus 4ac is a perfect square, we get rational roots. So all we mean by that is if we have a square root part, if that square root or the part under the square root is a perfect square, then it reduces down to a nice whole number, so I get an overall nice kind of rational or even whole number answers. The last little part, just to watch for and make sure you know for yourself, is if b squared minus 4ac is greater than or equal to 0, we get real roots. So each of these four things is really important, particularly the first three here. All of them are important, particularly the first three. The real roots idea here that we have comes from combining these two. So combining the first two, either of those scenarios gives me real roots. So let's just jump into it, looking at the nature of the roots of the following quadratics. We jump straight to our discriminant. So remember, we're using b squared minus 4ac for all of these questions. So for the first one, minus 6 squared minus 4 times 2 times 7. So I get 36 minus 4 times 2 is 8 times 6 is 56. So I get an answer of minus 20, which of course is less than 0. So that means no real roots. We can also say two complex roots or imaginary roots. Okay, looking at the second example here, same idea again, b squared minus 4 times a times c. 13 squared, 169, minus or plus 120. 289, this of course is greater than 0, so that means I have two distinct, and it's important to include that, two distinct real roots. So two different real roots, because remember, even if we have repeated roots, it's still considered having two roots. They're just the same root. It's two repeated roots. Let's look at the last example here then. Same thing again, 24 squared minus 4 times 9 times 16. So let's just work that out here. So 24 squared gives me 576. 4 times 9 times 16 gives me minus 576. So I get 0. And that means that I have equal real roots. Equal real roots, or sometimes one solution if you like. What we can do with these rules, besides something like that, just commenting on the nature of roots if we're given a quadratic, is actually to find ranges of values of x for which a quadratic has a particular type of nature. So for example, looking at this one here, given this equation, we want to find the values of k for which the equation has equal real roots. So remembering equal real roots, b squared minus 4ac is equal to 0. So that's what we jump straight to. So for b, that's going to be the minus 2k here. Minus 4 times a, which is 3. For c, this is the part that can be confusing. For c, we take this whole last section here, k squared minus 6. Remember, the c part is the part that has no x on it. So that's this whole section here. We want that part to be equal to 0. So 4k squared minus 12k squared plus 6 times 12. My brain's giving out on me, so let's go. 6 times 12, 72, of course. Okay, so we get minus 8k squared plus 70. When you write 76, 72. Let's divide by minus 8 there to give me minus 9. And I can solve that by difference of 2 squares there. And I get k is 3 or k is minus 3. So for either of those values of k, this equation will have equal real roots. What we also might want to show is the range of values, or show that a quadratic has a particular type of nature of roots for all values of some unknown. And this can mean what I've said here, manipulating the quadratic and using what we know about our mathematical rules and different kind of formula that we know to show that it satisfies the given rule. The main things we're going to be using is something like this. Anything squared is always positive. And we know that generally. You do have that idea. We mightn't have kind of stated it explicitly in that way, but we know anything squared is going to be positive. It's going to be greater than or equal to 0. So it comes down to, if we can write things as something squared, then we can show that it's always positive. Now I've put a note in here to say that this appears again in Algebra 3, and we go over things in a little bit more detail in that chapter. So just something to bear in mind for yourself as well, that we will go back over some of these ideas a little bit later on. So let's have a look at this question. So we're proving that the roots of this quadratic are real for all values. So real means greater than or equal to 0. It means that b squared minus 4ac is greater than or equal to 0 for all real values of h and k. So let's sub in. So for b, that's 3h minus 4 times a, which is 2, times c, which is h squared minus 2k squared. And I want to show that that's greater than or equal to 0. So I get 9h squared minus 8h squared plus 16k squared. I want to show that this is always positive. So I get h squared plus 16k squared. So at this point, it's not enough for us just to say, and yeah, lovely, that's always positive. We need to make a little note. H squared is always going to be greater than or equal to 0. No matter what h is, because we're squaring it, it's always going to be positive. The same thing happens here. This is always going to be positive also, because k squared, anything squared, is always positive. If I multiply it by plus 16, again, it's always going to be positive. So adding the two of those together, again, will give me something positive. So therefore, this equation 2x squared plus 3hx plus h squared minus 2k squared is always, has real roots for all values, for all h and k. Okay, so let's quickly run through some of these other points as well. So again, just the same thing again, show that the roots are real for all values of p. So again, we need to get b squared minus 4 times a times c. I want to show that this is always greater than or equal to 0. So 4 minus 4p plus 8, or sorry, skipping a part out here. So minus 4 times minus p squared plus 2p. And again, I'm trying to show that this is always positive. So plus 4p squared minus 8p, 4p squared minus 8p plus 4. I want to show that this is always greater than or equal to 0. Okay, so I'm trying to show that this is always going to be positive. The best way I can do that is to rewrite it as something positive. If I want, I could simplify the whole thing down here, simplify it down, or I can rewrite it as a perfect square. So if I jump straight into rewriting it as a perfect square here, the first part is going to be 2p, because that's going to give me the first part, and minus 2 gives me the second part there. I know it's negative because the middle part has to be negative. So 2p minus 2 all squared. If I wanted to, then I could also factor out a little bit more there as well, but we might just leave it as the 2p minus 2 all squared. Okay, so rewriting it as a perfect square there is the main thing, and again we're showing that that is always going to be greater than or equal to 0. Okay, the other thing we could do here is divide across by the 4, which is probably what we would do, and rewrite it as p minus 1 all squared. And again, that's always going to be greater than 0. So that's always positive. So we've proven what we want there. To show the roots are rational, well, for rational roots, b squared minus 4ac is a perfect square. And we have shown that to be the case here, because p minus 1 all squared is a perfect square. So the roots are rational. Okay, so again, we're just applying these ideas the whole way down here. So we're going to look at an exam question or two here then. The first one says, find the two values of m for which the following equation has exactly one solution. One solution, or one answer, one root, means b squared minus 4ac is equal to 0. Think about what it means in terms of what the graph would look like. It would mean that my graph comes down to the x-axis and only touches it at one point. So one solution, one root, equal real roots. So minus m squared minus 4 times 3 equals 0. M squared minus 4 times 3 is 12, times 3 is 36. So m minus 6, m plus 6. So I get that m is equal to 6, or m is equal to minus 6. That's my two answers there for that exam question. Okay, looking at the next exam question again, given that p is a real number, prove that this equation has real roots suggesting to me my discriminant greater than or equal to 0. Let's work out that discriminant. 4p squared minus 4 times a times c is, let me see now, I think I've made a little bit of a mistake here. So we need to start first of all by grouping things together. Okay, so I'm going to group the x terms so that I have a clearer picture of my equation here, because as you can see, these two terms are both our coefficients of x. We need to group them together to get the full answer of what b is. So 4p minus 1 squared minus 4 times a times c. So hopefully the rest of the equation then will be a little bit easier for us. And we want to show that's always greater than or equal to 0. 16p squared plus 16p plus 1 minus 8p greater than or equal to 0. 16p squared plus 8p plus 1 greater than or equal to 0. Okay, I need to show, sorry, I made a mistake here, this should be 8. Making mistakes left, right, center here. 16p squared plus 8p plus 1. This is why we shouldn't multiply out of brackets so quickly, but I'm trying to get through it a bit quicker to make the video a bit shorter. So 16p squared plus 8p plus 1 minus 8p. So obviously we're left with no 8p here in the middle and just a plus 1. A bit nicer for us there. Okay, same idea applies here. We just need to show that this is always positive. So this will always be positive. And if I add 1 to it, then the answer is always going to be positive as well. So therefore, our equation has real roots. Therefore, we have real roots always there. Okay, let's look now at the last exam question. So we have nice graphs, and this is just pushing us then to understand what we mean by each of these types of natures, and what we mean by having real roots or having equal roots, or what we mean by having no real roots. So the graphs of three functions f, g, and h are shown below. In each case, we have to state the nature of the roots of the function. Okay, we know roots of a function are where it crosses the x-axis. Okay, those are real roots. So if we look at these examples here, the one on the right has 2 points where it crosses the x-axis. So that to me says it has two real roots. And they're different roots. So we can even add in the word distinct there as well. So we have two real roots that are distinct. This example here, it touches the x-axis. So that has equal real roots, or we might say a repeated real root. The first example here doesn't actually touch the x-axis at all. We can see there's a bit of a gap between there. And what that actually means is it has no real roots. It doesn't cross the x-axis at any point. And we can consider that as being the same as complex roots. So no real roots means that it has complex roots. So we've kind of answered the question there for each of the examples. The first one has no real roots or has complex roots because it doesn't cross the x-axis at any point in the kind of real plane. The second example has equal real roots because it just touches the x-axis, it doesn't cross at any of those points. And the last one is two distinct real roots because it crosses the x-axis at two distinct points. The next one says this has equal real roots. We know equal real roots, b squared minus 4ac is equal to 0. So let's just sub in 4 times k equal to 0. So 1 minus 2k plus k squared minus 4k squared. Okay, 1 minus 2k plus k squared minus 4k squared. So I get minus 3k squared minus 2k plus 1. Let's divide across by minus 1 there. Okay, and again, I'm looking for now two numbers that will multiply to give me 3 but add to give me 2. So multiply to give me minus 3 but add to give me 2. So plus 3 minus 1. So taking out 3k, I get k plus 1. Taking out minus 1, I get k plus 1. So we get 3k minus 1 and k plus 1. So k equals 1 over 3 and k equals minus 1. So those are the two possible values of k for which that equation has equal real roots. So we can see the whole way down through those questions there, the key things for you to be aware of are this whole first box that we had. Okay, this whole first box, this is really, really important. So knowing how do I distinguish between the different types of roots that I have. So obviously we need to know that we're using the discriminant all the time, but also how does the discriminant behave for each of those types of roots. So knowing that it's greater than 0 for two distinct real roots, it's equal to 0 when I have equal real roots, so that one's kind of easier to remember. It's less than 0 when I have imaginary roots, and it's a perfect square for rational roots. Remembering as well what we've highlighted there, it's greater than or equal to 0 for real roots. That's combining the first two. We saw that one came up quite a few times. The second things to note are these sort of questions here where we maybe have to make comparisons or discuss a little bit more how the roots are behaving, proving that they're always positive, things like that. As I said, that aspect is something we will come back to a little bit later on. Equal real roots, put it equal to 0, solve the given quadratic. And the last little thing to be aware of as well is from this question here. How do each of the roots behave at particular points or particular points on our graph? So knowing what it would look like if a graph had no real roots, what it looks like if it has equal real roots and things like that. So all of these important elements in answering this question or questions of this topic.